Hello, everyone. Welcome to today's webinar. The title of our webinar is the high-speed design using CR8000 Design Force and Polar Speedstack. My name is Masoud Raisi. I'm an MC application engineer at Zuken. Today, I am delighted to represent Zuken in this hopefully exciting session. We are happy to have you join us as we will show you our collaboration with our partner, Polar. Our first speaker, Mr. Hermann Reicher, is a well-known expert in the field of printed circuit boards with a focus on impedances, layer stacks, high speed materials, and more. He will take you into the fascinating world of impedances and introduce one of the Polar's powerful tools, Speedstack, showing you how it can enhance your design process. Afterwards, I will show you the impedance handling within our product CR8000 Design Force, with focus on impedances and impedance constraining. And let's get started now. I will pass over to Mr. Reicher. Mr. Reicher, your stage
Thank you.
is yours.
Thank you, Masoud. Thank you very much. Thank you to the audience. Thank you for joining us today on our webinar on high-speed board design using ZR8000 Design Force and Polar Speedstack. My name is Hermann Reicher. I'm with Polar Instruments GmbH in Austria, responsible for technical sales and support of our products for signal integrity and multilayer stack-up design. The first slide of my presentation shows a typical PCB layout workflow. Every PCB layout starts with a pre-layout stack-up design where the number of layers are defined, the impedance requirements are defined, and the final thickness of the printed circuit board is defined. Once that information has been collected, a stack-up is created, and usually the information is transferred to the PCB layout system, either using the XML format or, for example, IPC 2581. Then the PCB layout work starts, and once that is completed, the final data is then transferred to the PCB manufacturer, often in formats such as XML, IPC 2581, or ODB++. In the pre-layout phase, often virtual materials are used as placeholders because only the thickness of the material is known, the final thickness of the board is known, but the designers often specify only the thickness of the copper and the dielectrics, but not the actual materials in the final stack-up. So that's why we call it placeholders. These are used to define the actual spacing between the reference layers and the signal layers. In the pre-layout phase, the final thickness of copper and dielectric is fundamental for simulating the impedance values. As we all know, the characteristic impedance of a PCB trace is defined by the trace width, the dielectric separation, and also by the dielectric constant of the laminate material. A dielectric layer is almost always composed of at least 2 plies of dielectric material to achieve the required thickness, and to achieve the required thickness and to reduce the risk of layer-to-layer shorts. By using two plies of dielectric or prepreg material, you do get a very good electrical isolation between layers. The PCB manufacturer then replaces the virtual materials by real available materials which he has in stock, and then simulates the pressing process to obtain the final thickness, depending on actual copper coverage and also the resin flow. And the final thickness is then used to calculate the required trace width and separation for a required target impedance. So as you can see in this slide, in the pre-layout stage, only the target thickness is defined, and once the data is transferred to the PCB manufacturer, he then actually replaces the dielectric region with, in this example, 3 plies of prepreg material, which give him the required final thickness. Controlled impedance specifications are usually defined by standards or by component data sheets. So the characteristic impedance is not something that the designer just deliberately chooses, but it's usually defined by the standards. In this case, for example, USB 3, which uses a 90 ohm impedance plus minus 15% tolerance, or SATA bus, 100 ohm plus minus 10%, or PCI Express. If we look at generation 3 and 4, we use 85 ohms plus minus 5%, or DisplayPort, 100 ohm plus minus 10% differential. So the designer uses this target impedance to simulate the trace characteristic and the trace impedance to arrive at the trace width required. Impedance categories, most impedance structures fall into different impedance categories. And in this slide, you can see a selection of different categories. For example, surface structures. In this case, a single-ended structure called surface microstrip, consisting of one trace and a reference plane underneath, a coated microstrip with solder mask on top of it, or also a differential coplanar strip, for example. The lower pictures show embedded microstrips, an offset strip line, or a dual or broadside coupled strip line in this case. In practice, we know around about 100 different structures which are used on actual designs, and these can be either surface or embedded, single-ended or differential structures. For impedance calculation, 2D field solvers are the tool of choice. Field solvers derive the actual impedance from the trace geometry and the dielectric material. Using a goal-seek function, it is possible to enter a target impedance value and extract the required trace width. A field solver also takes into account the cross-section of the PCB trace, meaning the trapezoidal shape, where the bottom of the trapeze is usually wider than the top, and the edge of the trace also affects the impedance, in particular with differential pairs. Transmission lines are considered lossy when frequencies exceed the frequency range of about 3 to 4 gigahertz. Field solvers are also capable of simulating the insertion loss based on dielectric losses and copper surface roughness. So in this example, you can see the red waveform, which represents the smooth conductor loss. The green waveform represents the dielectric losses, which, as can be seen, are dominating the overall losses. And the light blue trace just represents the total attenuation, including roughness, and as expected, the higher the frequency, the higher the losses of the transmission line are. Now, Speedstack multilayer software is a powerful stack-up documentation tool for creating and documenting multilayers, including drill information and impedance calculations. It is based on a field solver, and it is widely used in the industry, both with designers and also printed circuit board manufacturers. Speedstack accesses a very comprehensive material library containing all the material specification of major material vendors. And this material library contains all the relevant mechanical and electrical properties of the material, the dielectric base thickness, the finish thickness, the dielectric constant, and also the loss tangent of the material. This material library can easily be updated by downloading the latest material information from our website, and you can create your own library of preferred materials, or you can use the library that your PCB manufacturer uses of materials that he has got available in stock. Speedstack also includes a powerful design rule check, which makes sure that any violation of common stack-up design rules are flagged. And this includes stack-up symmetry, copper balance, drill aspect ratio, and resin starvation. These design rule checks may be turned on and turned off as necessary, but they make sure that during the stack-up process, all the fundamental design rules are being taken into consideration. Now, one important feature of Speedstack is the simulation of the process thickness. While the material library contains thickness information on the base unprocessed thickness, Speedstack is able to simulate the process thickness after pressing and plating. And the process thickness values are then used for accurate impedance simulations. So in this slide, you can see the actual copper coverage percentage for each layer, which is then taken as the base for calculation of the thickness after pressing. And also, the copper plating is added to all the layers that are connected to vias. The pressing process works using a simple method. Once the percentage copper coverage is known, that data is entered into Speedstack. And for example, if we have a 20% copper coverage, in this case, 80% of the copper thickness is pressed into the prepreg. And the liquid resin of the prepreg material is then used to fill the gaps between the traces. Remember, in the pressing process, the core material, the core dielectrics, are cured resin glass mixes, so they will not change the thickness during the pressing process. But the prepreg is an uncured material. It consists of resin and glass, and during the pressing process, the copper structures are pressed into the prepreg, which finally changes the thickness of the material. Now, to simplify the data transfer between the StackUp tool and the layout system, Speedstack offers a convenient way of export to Zuken ZR8000 design force, reducing time and eliminating human error. So by just choosing File Export and then Zuken ZR8000, we support a number of different versions, and export the StackUp that has been created with Speedstack and transfer that information straight into Zuken ZR8000, when the layout work starts. Vice versa, Speedstack also imports stackups directly from Zuken CR8000 DFM Center for further simulation and material specification. Remember, it is also possible to calculate the trace losses in Speedstack, calculate exact trace width for the required target impedance. So in all, the Speedstack Zuken ZR8000 design force data exchange ensures a transfer of layer stack data to ZR8000. It simplifies the documentation of stackups and material properties, namely base thickness, finish thickness, the permittivity, the loss tangent, and also the resin content. Design rule checks are put in place in an early stage of the design, taking into account the aspect ratio of vias, the build symmetry, and resin starvation. And finally, we are ensuring signal integrity on the final product by meeting the impedance requirements and also the delay of the traces. We also avoid a redundant documentation of material and impedance data because that set of information is simply transferred from one software package to the other. And finally, benefit from online access to high-speed material libraries. This high-speed database is always updated from all the major material vendors and includes all the latest materials, high-speed, low-loss materials that are currently widely used. This slide shows an example of a Speedstack printout showing the layer stack up on the top left corner alongside the material specification and the cross-reference to the impedance structures on each layer. The visual appearance of the printout may easily be adjusted to the customer's requirement, so the choice of columns, which information should be printed in the documentation can easily be configured. Each impedance structure is documented with exact trace geometries, and also target and calculated impedance is shown in the printout. Drill documentation for mechanical drills, laser vias, and also back drills is included. If you are interested in using Speedstack, by all means, do contact us for a free of charge demo license. We will be happy to provide you a time-limited license with full access to all functions and access to our online material library. This concludes my presentation. Thank you very much for your attention. And over to Masoud in this case. Thank you very much.
Thank you very much for your presentation, Hermann. So I would share now my screen directly. Now, what happens next with the layer stack data from Polar? The first step, I try to show you the flow for how it works based on really simple design in Design Force, CR8000. And I did some movies. I think if we see this in live, it's looked much better. So the first step is importing of Polar layer stack in CR8000 Word. So I start now movie, and here we are in the rule editor. So we define in that section our this description of the layer configuration. That means the thicknesses, materials, direct constants, and so on is defined in rule editor. And in this case, it's empty. We have only the technology file. And now we want to import the data from Polar Speedstack. And for this, we go to utilities and we have an import and also an export, the interface to Polar Speedstack. This import export is belong to the basic design force licenses, or is, let's say, is free of charge, the interface itself. So now I import the 6-layer templates from the Polar into the design force, and now I check the layer stack again, and now we can see the layer thickness is available, material so far it's defined is available, dielectric constants are available, and so we have now our correct layer stack in our system. The next step is creation of track width stack. That means we want to define how the width of the tracks are in our system, and this is done also in rule editor as well. We had the board configuration. Now we define our track specification. Here we can define the width stack, and you can use the configuration you already defined in Polar and type the values of the track widths. Another way is we have a field solver also in background, so just to check the impedances you can reach. So that means on layers 1, 3, and 6, we have this signal layers, and the reference layers are layer 2, 4, and 5. And therefore, if we want to have a lower impedance, we have increased the width of the track. Yes, that's now width stack with 127 micron. I set this as a default for the board, and the next track width is with 100 micron. We hope to reach something about 60 ohm, and then we get the near to 60 ohm based on layer stack we imported from Polar. In the same manner, we can define it for differential pairs. That means we can define the track width and the distance between the tracks, or track spacing. In this case, we aim to reach something about 90 ohms differential impedance, and define now the spacing of 100 micron, and we see, okay, about 90 ohm, and signal layers is possible. So we set it as active differential pair rule stack for the board, and also we use another one with 150 micron track spacing to reach 100 ohm differential based on information of the board configuration which we imported already. And then we see, okay, we can reach the differential impedance, and later we can use such our track width stacks for constraining. Good. That was the second step, and now that means we have imported the Polar layer stack. We defined our track width stacks, and now we want to generate topology templates and constrain the topology. This is the next step. So I have here really simple design. There are some pin-to-pin signals, and this one, the signal 50 is a branch line. So if we can see design, we have just six signals, and we have 4 components. IC1000 should be the driver, and IC1 the receiver. We create a new topology. That means we can define for single line or differential pair our topology templates. We need to define the number of buffers and a suitable name. I choose the name point-to-point and tree segmentation. That means I have a pin-to-pin templates with 3 segments. So I am now it's able to add some segments or passive, depends on the topology you want. You can create your template, and now we see that we have generated 3 segments, and here we see that we have now a virtual points between each segments. So now we are able to constrain this topology for the pin-to-pin signal, and now in this section, so we can select each segments, and this will be highlighted. So we can now define our length constraints for entire signal. That means from 120 millimeters to 125. As I already mentioned, it's just an example. And then for each segment, from the driver to the first virtual points, we define a length of pin pair length of 40, minimum length 40 millimeters, and maximum 42. And for the other side, from the receiver to the second virtual point, same length, and between the virtual points, we define 40 and let's say 45 millimeters. And now it's possible to assign our already defined routing bit stack to each segment. That means we can now say, okay, from the driver to the virtual point should be 60 ohm, because I will route with 100 micron, and the between the 2 virtual points, we want to have 127 micron to reach 50 ohm. Depends on data sheets you get and topologies you get from the manufacturer. And also you can define the minimum or maximum impedances for your topology. That means later, if you have a line which is routed over a gap, so you will get another higher impedances, so you can check your design against such constraints. The next topology is branch line topology. I would like to show you the virtual branch point, and so the name of this topology is now branch line with 3 buffers, and okay, now we have the pin pairs, and we can also define our pin pair length constraints and also the impedance constraints. So the each branch should be maximum between 130 and 135 millimeters. And from the driver to the first virtual point to the fork should be 50 millimeters, and so on, maximum 52. Okay, and also here it's possible now to assign our routing with stacks, so we can define our topology. 100 micron for each branch. So that means we created now a topology with constraining, and now we need to assign the topology to our signals and start routing. And that is now the next step. So we have now our signal. If we look in constraint browser, we now, okay, the pin pair, we have just 2 pin pairs because no topology is assigned. Now we select our topology we are interested in and define where is the driver, where is the receiver, from which side the topology should work. So we decided that our IC1000 is the driver. And now we apply this topology to our nets. Now we see the virtual points directly in design force. So that will help us later for routing. And we have now more pin pairs because the topology is assigned. So all information about the topology is now assigned to our signal. So there is no need to do something else. Everything is prepared because we did the work in definition of the topology. And okay, we can now select the other point-to-point signal. I will do it just for 3 lines. And then we go for the branched signal. And here also it's possible now to assign the topology branch line. And here we want to have the IC1000 as driver. So we select it. And now we assign this branch line topology to our signal. So the virtual branch point is now appears in design force on the corner. And now we have the possibility to place the virtual branch point. And as you can see, there are some other auxiliary squares appears here, which help you to find the best placement for the virtual branch point. That means so far you are in the, I will need to make it a bit bigger. Now I try to place the virtual branch point, and you see the auxiliary squares and the dashed lines means now you are in optimum placement, so you can fulfill the requirements. So then you can place your virtual branch point in the best position. And for other one, I will adapt this as well. So now we are finished with placement of virtual branch points. For other virtual points, there is no need to do something. So now we go for routing. I will apologize because I'm not the routing guy. I'm MC guy, and so I'm sure that a lot of people here can are able to route much better than me. But it's just show how it works in a flow. Okay, that means I have now routed one, and now I need to apply rules for track widths on that. So after execute this value, so we will see that the signal is now 100 micron. Now we have 127 micron and 100 micron at this side. So that means the topology we defined is now realized in the routing. in the same manner, we can route the second line. So such virtual points help us later, okay, for timing and to have the correct routing impedances. Okay, and now we route the last one. Oh, I have to apply the ruling and the width stacks. So now we have there's a correct routing here. So now I route to the virtual branch point. We try to meet the virtual branch point. And now I try from other side. Okay. And the last segment to the receiver pin of IC2. IC1, sorry. Okay. Okay, and the same manner we have to apply the track widths for this line as well. Now we see that each branch, here we have 127 and 100 micron for each branch. So that means from impedance point of view, we are now should be okay. So now in constraint browser, I select the signals and check once the routing with update value, we can check it. So we see that the match ratio is 100%. That means we are fully in range for our signals. We can check the pin pairs again for each segment with virtual pins and virtual branch points, and check the impedances. We are in range, but the pin pair lengths are not in range. That means we have some violations. That means the minimum pin pair length is not reached, so we need to match them. So I use now the intelligent router and try to adapt the values. So that's it's automatically happens. So and sometimes it's not. It's, the values you need to edit the values, so you can select the section and edit edit the length and the form of this. So now we can say, okay, please meet the constraints, and then we are able to edit this pattern. And we maintain meet constraints. So then you can try to find the optimum position for your lengthening pattern. Okay, now the branches here. So meet constraints again, and also here is possible to change them and modify them. Okay. Now we modified the pin pairs, so we hope that the pin pairs length constraints are fulfilled as well. So we can check this in constraint browser against the pin pairs from the topologies. So we see, okay, the I select the signals and we see, okay, the values are correct. I have some violations in micron. So you can refine the lengthening if it's necessary later. The name is TDT and look at the receiver side and check the timing of timing behavior, electrical timing lengths of the signals. So this can be also used as well. And now I will come to my last slide. I was told to use the opportunity and add an advertising block to inform you about our Zuken's MC services. So we offer also EMC consulting and try to support you during or after a design to improve the SI and PI behavior on your design. For example, we can support you with simulation of high-speed interfaces like microcontroller on memories DDR4 or low-power DDR4, or give you hints to reduce the design failure. So we also offer SI and PI basic and advanced training for PCB designer. So if you are interested in such services, please contact us. And now I'm the last slide. I would just look to the questions. Is the copper position above, below, also imported and updated? At the moment, unfortunately, no. The copper position is need to be modified manually. This is something we are working on. That is enhancement, and we try to enhance this one. When importing the Speedstack file into Zuken, do the layer name. No, the layer name is not important. So we take our own layer name. How is the rise time given for TDE? Can I? Yes, you have the possibility to use your own model for TDR simulation, or you can use our defined rising time. So we have between 10 and 100 picosecond. So that's no problem. You can do your own TDR model as well. Does Zuken have standard layer configuration for 2, 4, 6, 8? No, we have no standard layer configuration, unfortunately. The application engineer, yes, we have, but we did it by ourselves. Is the way that instead of manually typing trace widths into the rule that you can import them from Polar? It's a good idea. Not yet. Sorry, that's not possible. Not yet. That means you have to put it at the moment currently manually typing. But this could be a very good enhancement. We need to talk about this Herman later. How is handled if we import layer stick up with real material? With real material, that means and multiple types of prepreg stacked on one Telecom tools here. Yes, at the moment it's only possible to have one Telecom. So this is also an enhancement request, but we can add the materials and try to set a value, an average value for the dielectric constants, and work with this. So that's a good approximation.
Yeah, this could also be done by re-exporting the stack from Zuken into Speedstack and then replacing the dielectric region with single plies of prepregs, for example. So that can be achieved.
Yes, yes. Can I know how it is the 10 and 100 because the rise time value considered in general? We calculate from bandwidth and differs. So this is up to you. You can define your own model, or you can use our models. So for TDR, I think this is the question. So related to this, you can email me directly, so we can exactly discuss about this. So because I see that's Mr. Oval. Hello, are wire types in Speedstack class? Hello, are wire types in Speedstack classified after IPC standard 4761? Hermann?
Yes, they are. Speedstack allows, in general, all types of vias, whether it's mechanical vias, micro vias, buried vias, stacked vias, staggered vias, back-drilled vias, filled vias, covered vias. There's a whole range of vias available, and they're all part of Speedstack.
Are there plans to implement ChatGPT functionality to design force? Mr. Kohlinger. Not yet. No, sorry. It's not planned. I don't any plan or schedule for that. Setting up topology sounds good for flexibility. However, I don't understand this concept. Could there be some info available of how to set this as well? Good trace. Yeah, yes, please ask us. Okay, I don't know. Maybe you send me an email exactly what do you want to have with flexi rigids. But this would be work for this topology assignment works for the signal. So that's independence of
Maybe I can add to
any.
that.
Yes, please.
Speedstack is also available in a flex version, so it does support flex rigid stackups, maintaining the constant impedance throughout the whole signal path when the signal runs through the rigid part and then enters the flex part and back into the rigid part. Speedstack takes care of the whole signal path and calculates the required trace width for each segment just to make sure the signal sees the same impedance when it transverses from rigid to flex to rigid.
Then we have another one. Is it possible to get the exported Polar Speedstack data? The exported Speedstack. Yes.
Yeah.
This is what we did. That is the
Um,
XML file, and
if,
we imported in CR8000. Yes.
mhm. It's
Correct.
it's not a binary format. It's an XML format. It can be opened with a text editor or with Microsoft Excel, for example. So it's a transparent format. It's not encrypted. It's not binary. It's an open format.
Does it make a difference calculating impedances with Polar versus Zuken?
Maybe I
Good
can.
point. It is. Yes, please. Maybe you can
Maybe I
answer.
can add to that. Both tools are using field solvers. Field solvers are the tool of choice for impedance calculation. The main difference in the results are which parameters are taken into account. So, for example, the multiple dielectrics. Is the field solver capable to take into account a mix of different dielectrics? Does it take into account the profile of the solder mask? Does it take into account resin-rich areas and so forth? So I would answer this as yes, both field solvers are very accurate, but each field solver is only as good as the data that you feed into the simulation. And
Fully correct.
yeah.
Yes, I can only confirm Mr. Reicher's answer.
Yeah. As long as you use a field solver, they are usually accurate to about 1 ohm, and that's good enough for most applications. What I would like to point out is try not to use approximations that you may find on the internet. Make sure you use a proper field solver. Yeah.
Okay. Now we are run out of time, so time is over. And I see I have some people. Most of them are from Siemens. Mr. Domke, Günes. I will ask you your questions afterwards. So that's something for Zuken side. Okay. Okay. Thank you all for attending today's webinar. We hope you found the session informative and useful. If you have any further questions or need additional information, please don't hesitate to contact us. I have an additional information for all people located in Germany. Next week is the FED exhibition. We can do it in German, FED-Messe in Ulm. So you all have also the chance to visit us, Polar and Zuken, Mr. Reicher and me, we will be available, and looking forward to see you in Ulm if possible. And okay, wishing you a wonderful day ahead. Goodbye and take care. Bye bye.
Thank you for joining our webinar. Thank you so much and see you soon. Bye bye. Thank you.
Bye bye.